For this special edition, we have two astronomers with us. Asteroid Day, of course, our first astronomer is our amazing astronomer that is just 2 doors down from me on the unceded territory, the Musqueam, Squamish, and Tsleil-Waututh. That is Marley. Hey, Marley, how's it going?
It's good. I'm boiling to death in the office, but it's not summer if I'm not doing that. So
That's how it goes for Asteroid Day, which is always celebrated on June 30th every year. We'll get into why that is. So that explains why it's so hot. But for this special edition, we have another astronomer, one that is a little bit younger than you, Marley, and that is someone who just won platinum at the Canada-wide Science Fair for their project on asteroid detection. And that is a student from Toronto, Arushi Nath. Hello, Arushi.
Hi, it's great to be here.
Thanks for coming on the show. So we're going to get into your project. So first off, I just want to get some of your thoughts. You are a platinum winner. You're actually a back-to-back winner at the Canada-wide Science Fair. How is that feeling for you after it must be so much work to do these projects on top of the schoolwork that you're already doing? How's that feeling right now?
Yeah, it was definitely very exciting to hear my name called up as Best Project Award winner. And, I had spent over 800 hours on my project. So it was amazing to see all that hard work paying off. And to have it 2 times in a row, that was just, wow, amazing.
Marley, were you ever a science fair kid?
no, I was not. I did not go to. I was not. I don't know. It just never came up, I guess.
It's certainly a lot of work, but it was certainly an amazing experience to see the energy of the room and to see so many diverse young voices out there. It certainly gave me hope for the future. And certainly we are talking about the future in asteroid detection because that helps protect us. We are talking about planetary defense, essentially protecting us as humans from potential catastrophe. So that's kind of like the theme for today. If you were out there watching on YouTube land or on Facebook, this is the theme we're going with asteroids. But if you have any question under the universe, put it into the chat. We will answer all of your questions until we get to the half-hour mark today. Well, Asteroid Day, Marley, what are we talking about here? Why are we celebrating large rocks in space?
It's not necessarily a celebration unless you're me, because it means I get to watch Armageddon without judgment. But it's more so a commemorative event, right? So recognizing to mark the Siberia Tunguska event, which was this large event that we think happened probably in 1908, June 30th, when this large asteroid burst in the air, right? A meteor air burst is what it's called, burst in the air, and it actually leveled, 2,150 square kilometers of forest, right? So trees were just leveled, cut completely. And so it's to commemorate this day and to kind of recognize that, we are a rock in space, kind of doing our thing, but there are lots of other rocks in space also doing their thing. And one of the big parts of Asteroid Day is this 100 times or 100x commemoration, right? Or the declaration, which is a call for increase in the rate of discovery 100 times within the next 10 years, right? So increasing our abilities to discover these asteroids, and by discovering them, also studying them and monitoring where they're going, what their orbits are, and if they could produce any potential hazards to Earth and to our planet. And as of now, there's 208 different signatories on that declaration, including Canadian astronaut Chris Hadfield has signed on, which is great to hear and great to have.
Wonderful. So we're a rock in space. I love that analogy. And rocks are doing their thing, and they're out there, but some are coming close to us, and that's something that makes me a little nervous sometimes. We hear lots about them, especially when we discover them recently. And the idea is that we can discover them further away and actually give us time to do things. There's lots of science fiction television shows, movies, literature that have explored this idea. What can we do? Well, step one is to find them, detect them. And that's kind of where Arushi comes in developing some of these algorithms. So Arushi, why don't we give it over to you? And I'm just going to quickly answer a quick question we got here on YouTube. Someone asked if I'd ever been a science fair participant, and that is no. I was a nerdy kid that we didn't really have many opportunities at my school. However, I will let you know that as an adult, I did a science fair project just out of pure curiosity on the speed of sound. So we can talk about that under a later episode. But for now, let's go to the double platinum winner, and that is Arushi with their project on asteroid detection. Take it away, Arushi.
Sure, thank you so much. So my name's Arushi, and for the last 2 years, I've been doing Canada-wide Science Fair projects, both based on classroom defense. So in 2022, I made a project on detecting unknown asteroids. So what I did there is I created an algorithm to basically look at images of the sky and then try to find unknown objects. And then this year, I continued upon that. And this year's project was on creating algorithms to analyze these asteroids and find the physical properties of all near asteroids. So I'll be talking a bit about this year's project. So first, it's important to say that asteroid collision risks are real and collisions can happen sometimes. Like we've seen 66 million years ago, the Chicxulub asteroid completely wiped out the dinosaurs. And just a few months ago, last year in November, an asteroid whizzed past the CN Tower, very close to my home actually, and luckily it landed harmlessly in Lake Ontario, but this showed that asteroid collision risks are real. And hundreds of near-Earth asteroids continue to be discovered every month. And if one of these asteroids were on collision course with the Earth, we would need to know their physical properties, like their size, what they're made of, their strength, and if they have a moonlet to be able to deflect it. But unfortunately, there's not enough professional astronomers currently to analyze all these new asteroids fast enough. So that's where my project kind of came in. I had three main goals. So first, I wanted to develop algorithms to basically find the physical properties of asteroids, and I want to make them in such a way that can be used by anyone, so citizen scientists and backyard astronomers. Second, I want to apply my algorithm to a real-world scenario to determine the physical properties of the Didymos binary asteroid. And third, I want to apply my algorithm to measure the success of NASA's double asteroid redirection test mission in deflecting the asteroid Didymos dimorphos. So how did I go about this? So I'm going to now give a quick overview of what my algorithm and I basically did to find the physical properties of asteroids. So the first important thing is I want to be able to image the asteroid continuously to get time series data. So to do this, I sent research proposals to telescopes located all around the world, in places like Australia, Chile, and United States, to get time to observe the asteroid. And in whole, I made over 55 hours of observations, spread before, during, and after the DART impact. And then I created my own algorithm in Python to analyze these images to find the physical properties. First, what I did is I took my images and pre-processed them. So this included finding all known objects in my image, so known stars and asteroids, and then centroiding them in my image. Next, now that I had my centroided asteroid in the image, in this case it was Didymos dimorphos, then I wanted to basically find its brightness. So to do this, I created apertures of different sizes around the asteroid. I created an inner aperture to measure the brightness of the asteroid in pixels, and I created an outer analyst to measure the background noise. I then subtracted the two to find the actual instrument magnitude of the asteroid. But this wasn't enough because sometimes my observations were very long, so 3 or 4 hours, which meant that observing conditions could and did change. This could include air mass or simply weather conditions like a cloud passing in front of the image for a couple hours. So how did I account for this? To account for this, I used comparison stars. So these are stars with known and constant brightness. So by measuring their change in instrument magnitude caused by the weather, I could apply this to my target asteroid to measure basically its brightness without any changes in weather, so in ideal conditions. And this is called computed magnitude. But there was still one other main step to do, because asteroids are always in movement, which means as they move, their distance from the sun and their distance from the Earth changes. So to account for this, I found the absolute magnitude of the asteroid. So this is its brightness as if it were one astronomical unit from the sun and the Earth and at a zero phase angle. So this allowed me to get time series brightness of the asteroid where the brightness only changed because of the actual physical properties of the asteroid. Then, using this, I was able to find both the rotation and mutual orbital period of the asteroid. Because as asteroids rotate, different sides reflect light differently, causing 2 maximums and 2 minimums in their light curve. So, I was able to create an algorithm which used modulus, so remainder, to basically find exactly the rotation period of the asteroid by testing different intervals, in this case from 2 to 5 hours. Then, by subtracting the rotation period from the main light curve, I repeated a similar process, this time to finding the mutual orbital period. So I got several results. First, I found the absolute magnitude of the asteroid to be 18.03 and its size 820 meters. Second, I found the rotation period of Didymos to be 2.26 hours by calculating, basically looking at all the intervals and then looking at combining all my individual observations and seeing which one had the smallest root mean square error. So I found it was 2.26 hours and did not change post-impact. Third, I measured the mutual orbital period of the system, so basically how fast Dimorphos was orbiting around Didymos, and found it to be 11 hours and 55 minutes, and it actually reduced by 35 minutes after the impact. Fourth, during the impact, I also measured some changes. Right after the impact, there was a surge of 1.2 in the magnitude of the asteroid system, caused by all the debris and ejecta around the asteroid, reflecting sunlight. And due to the ejecta, I also noticed a 20,000 kilometer long tail coming from the asteroid. And using the rotation period and the size of the asteroid, I was also able to find that both the main asteroid Didymos and the moon-led Dimorphos have to be rubble-based. So now my final result, the big question: did we move Dimorphos? Judging by the 35-minute decrease in the orbital period of Dimorphos around Didymos, this translated to a 40-meter reduction in its orbital radius, proving that the asteroid deflection was in fact successful. And actually, for your information, the DART mission was the first kinetic impact test to basically see if we can deflect an asteroid. So it was great to see it was successful. And all the results from my algorithm were able to get validated by external sources, such as NASA. I have done lots of outreach for my project. I've published my algorithm as a 4-step training module on GitHub, and I've actually started to receive requests from professional astronomers asking me to analyze other binary asteroid systems whose new data has just become available. So in conclusion, I was able to develop an algorithm that can be used by anyone to find the physical properties of asteroids, and I was able to apply it to measure the success of asteroid deflection. Citizen scientists can now use my algorithm to become planetary defenders by increasing the pace of analysis of near-Earth asteroids. One quick news I would like to share is I was able to go to the Planetary Defense Conference in Vienna about a month ago and present my research. But the most amazing part was hearing from several other international delegates who were also interested in planetary defense. So just a quick background on the Planetary Defense Conference. It's a conference that happens every 2 years, which mixes planetary defense, so astronomy, as well as politics, to try and characterize asteroids and see what would happen during asteroid deflection. So one or two takeaways is an important question. What would we actually do if an asteroid were on collision course? How would we deflect it? And this comes down to two main properties about the asteroid. First is how big it is, and second, how long do we have till it impacts the Earth? So if we have a long warning time, so above 5 years, we have several different options. If the asteroid is small, so under 200 meters, then we could either use a single kinetic impactor, or we could also use a gravity tractor. So this would have been used in the case like a Dimorphos-sized asteroid if it were a collision course with the Earth. Both these options would be possible. But what if the asteroid is bigger, above 200 meters? In this case, we would send several kinetic impactors to the asteroid to try and deflect it. But now the question comes, what if we don't have much time? What if the impact time is in less than 5 years? Then we really don't have much choice. Nuclear weapons is the only possible chance we have at deflecting it. But there's also legality issues that come up when deflecting asteroids. Let's say an asteroid were on collision course with the Earth. We would first need to know if the country where the asteroid was going to impact, do they have their own deflection techniques? And if they do, what would happen if the deflection was not successful? Or more importantly, what would happen if the deflection was only partly successful? So it impacted maybe another region of the Earth instead of the original country. Then so many legality issues would come up. And the country that launched the deflection would be in several problems. Because there are several actually laws that contradict using nuclear weapons in space. So it really comes like a big decision to make here, whether to act or not to act. So those were just a few key takeaways. And after 800 hours of hard work on my project, I was so happy to be selected as a finalist at the Canada-wide Science Fair and to be able to win the Best Project Award. I will also be presenting my project in the upcoming NASF or NASA Exploration Science Forum in Maryland just in a couple of weeks. And I will, as a winner of the Canada-wide Science Fair, I'll get to go to Belgium to present at the European Union's contest for young scientists and compete with international finalists. So that's a quite exciting opportunity that I'm looking forward to. And just some future goals. Well, in the future, I would like to expand my algorithm to other planetary defense missions launched by China and Japan. And the interesting thing about these missions is these are targeted at smaller asteroids, about 20 or 30 meters, whose actually impact probability is the highest. So it's important to know a lot about these asteroids. And I would also like to combine my robotic telescope observations with radar observations to be able to perform shape modeling on the asteroids. So thank you so much.
Awesome. Thank you so much, Arushi. That was amazing. If you're out there and have a question for Arushi and her project, put a question or a comment into the chat, whether you're on Facebook or on YouTube. Arushi, I want to, this is amazing. You say 800 hours and you are a student, you've got so many responsibilities, and you're learning already, and this is on top of all of that. Your life must be pretty full. Do you have any hobbies beyond sort of, just scouring through amounts of data, looking for asteroids?
Yeah, for sure. I have several hobbies, like I do rock climbing and water polo and occasionally play the piano. But also a new passion I've developed is becoming very politically active in my city. Yeah. So campaigning for progressive candidates, both city councilors and mayor candidates. Like the mayor election for Toronto was just a couple of days ago, which was pretty exciting. So yeah, that's some new passion I've developed.
Wonderful. And why asteroids? Was there a reason, like as a young person, that we see a lot of young people come through here at the Space Center that have lots of curiosities. We don't often hear young people talking about asteroids. What drew you to them?
Well, I think asteroids are a very unpredictable subject when you think of it. Their orbits can sometimes be very uncertain. We don't know all the asteroids yet in our solar system. And if an asteroid does impact the Earth, it could be a very big disaster. So I think all of these stuff merged together kind of increased excitement for this part of it. And that's why I chose kind of like the path of planetary defense, protecting the Earth from asteroids as my topic to go towards.
Nice. Marley, do you have any questions for Arushi?
Yeah, I wanted to see, could you show the slide again of the brightness curve, like how you did that, because that was very cool. Because the telescopes you're using, I didn't get a chance to see how much time you had, like your observation time to be able to detect the brightness.
Yeah, for sure. So these are basically, is the slide you're talking about?
Yeah, rotation period. Yeah.
Yeah. So here the interesting thing is I was able to get observations from robotic telescopes over several nights. So these were spread over before, during, and after the impact. And for each period of time, what I did is I set the intervals. For example, for rotation period, I said the rotation period must be between 2 and 5 hours. And what I went about this is I tested basically thousands of points between those two intervals. And for each one, I combined all of my rotation period light curves into one constant curve. And for each, kind of determined the curve fit, as you can see in the solid red line here.
Okay. And the red is your fit. Okay.
Yeah, the red is the curve fit. And basically found the root mean square error of the points from the curve fit. And the curve with the smallest root mean square error was my actual light curve.
Right. Okay. Nice. Very cool. I love a graph. So
That's true.
Big fan of graphs, big fan of light curves.
Arushi, you mentioned, citizen science in your presentation, and of course, this is where you came into this, right? Like this data was accessible to you. Could you maybe explain for those out there that might not understand how that works, right? There is data that these telescopes are getting, and you and other people have access to using them, or did you actually have to go through a process to use some of this data?
Yeah, so in my case, what I did is I made use of both my own data as well as data that's publicly available online. So what I did is basically I wrote proposals to robotic telescopes who gave me time under telescope to freely observe the sky as I wished. And then basically I pointed the telescope to a specific asteroid and then took long time series observations of the asteroid over time, which by the way, all telescopes share and are publicly available. So you can always see their archive of data. And I've also published basically the raw light curves I was able to get from those observations on the AlcDef database, which is basically an asteroid light curve database, which keeps track of light curves of many asteroids in our solar system. And for datasets that are already available, this was very useful in the preliminary part of my project, where I was trying to find basically all known objects in my image, so known stars and known asteroids. So here I used open datasets that are freely available from both NASA and the European Space Agency. So I used NASA's Horizon dataset to basically find the positions of any asteroid at any given time, because of course asteroids are always moving, so their position will always change. But based on their orbit, you can kind of predict at what time will they be in what position. And I used European Space Agency's Gaia database to find known stars in my image. So basically by looking at the coordinates of all known stars and then knowing basically where my image was exactly. So feeding that information in the database and using an API query in Python to basically query which stars are in my image.
Wonderful. So Arushi, we've got a couple of questions online that we want to get to. I'm curious, did you just finish, because school just ended, a few days ago for you. Did you just finish grade 8 or grade 9?
I just finished grade 8, so I'm going in high school next year.
Going to grade 9 next year. So you've got a few more years left of your science fair career, because you can continue on until like grade 11. Is that something that you want to do?
Yeah, I'm definitely thinking about going to the science fair next year again. Still thinking about what type of project I do, or whether to stay in astronomy or go to something different.
Yeah. Do you have any thoughts yet?
Oh yeah. I'm thinking of going switching from asteroids to go towards exoplanets. So basically kind of like solar systems that are not our solar system. So here what I want to do is to try and measure basically find exoplanets in our sky and basically look for their atmospheric compositions. So this is basically using basic transit methods and see where I can go from there. Because several interesting telescopes have just been launched or are going to be launched soon, like the James Webb Telescope or even the Ariel Telescope that's going to be launched in several years. So many new telescopes are being launched, which are specifically related to looking for exoplanets. So I think it's a pretty hot topic right now.
Yeah, and this isn't, obviously I mentioned that you were a back-to-back winner, so you had a project that won platinum the previous year. Was that also on asteroids?
Yeah, that project was on the detection of asteroids. So there too, I used robotic telescopes to image the sky, but then my primary goal was to find the unknown objects in the image. So I followed a process of elimination. So I eliminated all known stars and all known asteroids, so asteroids which had already been discovered. And basically analyzed the rest of my image, removed all camera noise, all other sources of noise, and found all unknown objects in the image which were left over. And from there, I submitted my observations to the Minor Planet Center, and 3 of my observations were classified as preliminary asteroids.
Awesome. So do you get a chance to name those asteroids because you found them?
Unfortunately, no. They didn't move on to the next stage since there were no new discoveries of that asteroid in the next couple of weeks. But hopefully I'll be able to apply my algorithm on maybe some other images and find some unknown asteroids.
Do you have any nicknames that you called them yourself? Like if I found an asteroid, like I'd be naming them. Like I'd be naming like Daryl Strawberry, Luke Skywalker, things like that. But that's kind of a big nerd.
Yeah,
maybe,
of course.
maybe Nickelback, Marley.
Yeah, naming asteroids, you do have to follow a special convention, like 4 numbers and 3 letters, I believe.
Yeah.
So like showing the year and also based on like kind of the time you just detected it. So sometimes you get a choice, sometimes you do not.
Yeah.
Okay. I was just thinking about like, what if an asteroid was actually made of nickel? That would be an amazing name for an asteroid. So I guess this is leading me to the next question. Of course, like we talk to a lot of kids your age that come through here, and quite often they are thinking about what they want to do next when they actually get to do like not real research. You've been doing research, but like university level research in your university career. Is that something at this stage that you're thinking about? Like you're kind of dabbling in a few different subjects and you're probably going to have lots of options available to you where you want to go. Is that something you're thinking about now?
Yeah, for sure. Like currently, since I have lots of free time on my hands, like I just finished middle school where you basically have no schoolwork, no dedication to school or at all. So I had plenty of time to work on different subjects, see which one really passionates me. And so for now, I'm thinking I want to go into astrophysics, astronomy, aerospace in the future in university. Still haven't fully decided, but that's the path I'm looking towards right now.
Awesome. Well, I'm sure the university out here, University of British Columbia, will be wanting to pull you in. They have obviously deep connections there with exoplanets. That's where Marley came from, and obviously followed their career. Arushi, this has been amazing. Thank you so much. Good luck with the future. You're going to Brussels in September, you said?
Yes.
Wonderful. Well, we wish you luck. Hopefully we will talk to you in future years for your future projects. Thank you for joining us in this edition of Ask an Astronomer.
For sure. It was great being here. Thank you.
Awesome. So for Marley, we will be back in a couple of weeks on July 13th. That's actually where we're going to have our drag show. If you are in Vancouver and you are looking to see a space drag show, July 13th is going to be a really special one. Those tickets are actually going to be posted tomorrow, I believe. So head to our website, spacecenter.ca. To get tickets for that. That's going to be really fun. And then, of course, August, we have two amazing events. One around Tanabata, which is the Japanese Star Festival. We're going to be doing some cool stuff with the Powell Street Festival that weekend. So August 4th and 5th, we're going to be doing a presentation here in the planetarium on August 4th. And I will be out at Oppenheimer Park, which is where the Powell Street Festival is going to be with the Portable Planetarium on August 5th. And then the week after that, we've got the Perseids meteor shower. Speaking of tiny little rocks doing their thing around space, we will be doing, again, a special presentation on August the 11th here in-house, and then we'll be going out to Aldergrove Regional Park. You know, of course, you need to be in a dark sky to see these tiny little things burning up in our atmosphere. That's one of the best places in the Lower Mainland. But you can just find any dark place you can. Get out there, find something nice to drink, lay down in a nice park. That is the best place to view the meteor shower. We're going to get into all of that leading up to August. So for that, Marley, Arushi, thank you both very much. Happy Asteroid Day for all of you in YouTube and Facebook land. We will see you in 2 weeks. Take care, everyone.